Hello students, in today's lecture we will learn about conductance of electrolytic solutions. This is a lengthy section and please listen to my lecture very carefully. You may get one or two questions in your competitive examinations from this section. Please listen attentively and note down all the important points. I welcome you once again. Conductance of electrolytic solutions. It is necessary to define few terms before we consider the subject of conductance of electricity through electrolytic solutions. The electrical resistance is represented by letter capital R and its unit is ohm. That is the Greek letter ohm as shown on the screen. It can be measured with the help of a Wheatstone bridge about which we have studied in our physics class. The electrical resistance of any subject is directly proportional to its length L and inversely proportional to the area of cross section A. That is, it can be written in mathematically R is proportional to L by A, where R is the resistance, L is the distance between the plates and A is the cross section area. And eliminating the sign of proportionality, we can write R is equal to rho into L by A. Let it be equation 1. The constant of proportionality rho as written in the equation 1 is called resistivity, or it is also called specific resistance. The SI unit of resistivity is ohm meter and it is written as ohm meter, and its submultiple is ohm centimeter, which is used in many cases, practical cases. IUPAC recommends the use of the term resistivity instead of specific resistance. So we are using the term resistivity. Physically, the resistivity for a substance is its resistance when A is equal to 1 meter square and the distance is length is 1 meter. So we can write, it can be seen that 1 ohm meter is equal to 100 ohm centimeter, or 1 ohm centimeter is equal to 0.01 ohm meter. So if you put L is equal to 1 meter and A is equal to 1 meter square, then R is equal to rho. Hence, we can define the resistivity of a substance is its resistance when L is equal to 1 and A is equal to 1 meter square. The inverse of resistance, that is 1 over R, is called conductance and it is represented by letter G. Its symbol is G. So for conductance, we write the letter symbol G. Therefore, G is equal to 1 by R, that is reciprocal of the resistance. That is equal to substituting the value of R from equation 1, we get G is equal to A over rho L. That can also be written as kappa into A over L, where kappa K is equal to 1 over rho. So in this equation, if you put 1 by rho is equal to kappa, then G is equal to kappa into A by L. Let it be equation 2. The SI unit of conductance G is Siemens and it is represented by symbol capital S, and it is equal to inverse of ohm, ohm inverse, or ohm per ohm. Also, it is known as inverse of ohm is mho, mho, or per ohm, ohm inverse. The inverse of resistivity is called conductivity, that is specific conductance is represented by symbol kappa k. In this equation 2, kappa k is the conductivity. IUPAC has recommended the use of term conductivity. The SI unit of conductivity is Siemens per meter, but quite often kappa is expressed as Siemens per centimeter. Conductivity of a material in Siemens per meter is its conductance when it is 1 meter long, that is L is equal to 1 meter and area of cross section is 1 meter square. That is, if in equation 2 we put the value of A as 1 meter square and L as 1 meter, then kappa is equal to G. So we can say that conductivity of a material is Siemens per meter is its conductance when A is equal to 1 meter square and L is equal to 1 meter. It may be noted that 1 Siemens per centimeter is equal to 100 Siemens per meter. Conductors, insulators, and semiconductors. All materials can be classified into three different parts like conductors, insulators, and semiconductors depending on their magnitude of conductivity. Conductors. Metals and their alloys have very large conductivity and are known as conductors. Certain nonmetals like carbon black, graphite, and some other organic polymers are also electronically conducting. So please see the table number 1 shown on the screen. So the conductors are listed in the first column and only one. These conductors may be sodium, copper, silver, gold, iron, and graphite. And the value, numerical value of conductivity in Siemens per meter is also shown respectively. For example, sodium has conductivity of 2.1 into 10 to the power of 3 Siemens per meter. Insulators. Substances like glass, ceramics, etc., having very low conductivity are known as insulators. So, substances which have low conductivity are insulators. The insulators are tabulated in column number 2, last but 2 rows. That is, insulators are here glass with a conductivity of 1.0 into 10 to the power of minus 16 Siemens per meter. And similarly, Teflon, which is another insulator, has conductivity of 1.0 into 10 to the power of minus 18 Siemens per meter. Semiconductors. Substances like silicon, doped silicon, and gallium arsenide having conductivity between conductors and insulators are called semiconductors and are important electronic materials. In the case of semiconductors, the conductivity lies between the numerical values of conductivity of conductors and conductivity of insulators. So, the semiconductors have a conductivity between conductors and insulators, and these are called semiconductors. The value of semiconductors is also shown in the table number 1. The last three cells, that is cuprous oxide with a conductivity of 1 into 10 to the power of minus 7 Siemens per meter, as well as silicon has a value of conductivity 1.5 into 10 to the power of minus 2, and germanium has a conductivity 2.0 Siemens per meter. In addition to the above three classifications, we have superconductors. Certain materials called superconductors by definition have zero resistivity. So, in the case of superconductors, the resistivity is zero, that is infinite conductivity. That is 1 over 0 is infinity. Earlier, only metals and their alloys at very low temperature of the order of 0 to 15 Kelvin were known to behave as superconductors. But nowadays, a number of ceramic materials and mixed oxides show superconductivity at temperature as high as 150 Kelvin. Electrical conductance. Now we will study the difference between the metallic conductance and conductance of an electrolyte. First we will take up the electrical conductance through metals. Electrical conductance through metals is called metallic or electronic conductance, and it is due to movement of electrons. Please note that the conduction through metals is due to movement of electrons. The electronic conductance depends on the following factors. Number 1, the nature and structure of metal. Number 2, the number of valence electrons per atom. Number 3, temperature. That if there is an increase of temperature, the electronic conductance decreases. Please note that as electrons enter one end and go through the other end, the composition of metallic conductors remain changed. That means there is no chemical reaction and the composition is unchanged in respect of metallic or electronic conductor. The mechanism of conductance through semiconductor is more complex. We already know that even very pure water has small amounts of hydrogen and hydroxyl ions which lend it very low conductivity. Electrolytic condenser. In serial numbers 1, we studied the characteristics of electrical conductance through metals. In serial number 2, here we will study about electrolytic conductance. When electrolytes are dissolved in water, they furnish their own ions in the solution and hence its conductivity also increases. So, when electrolytes are dissolved in water, its conductivity increases due to increase in ions, number of ions. The conductance of electricity by these ions present in solutions is called electrolytic or ionic conductance. So in the case of electrical conductance, it was through movement of electrons, whereas in the case of electrolytic condenser, it is due to movement of ionic particles, ionic or electrolytic conductance. The conductivity of electrolytic ionic solution depends on the following factor. Number one, the nature of electrolyte added. The size of ions produced and their solvation. So, in the case of electrolytic condenser, ions are produced and the size of these ions is responsible for conductivity of electrolytic ion solution. Number three, the nature of the solvent and its viscosity. So, conductivity of electrolytic solution depends on the nature of the solvent and its viscosity. The conductivity in the case of electrolytic solution also depends upon concentration of electrolyte. Finally, the conductivity in the case of electrolytic solutions also depends on temperature. However, in this case, the conductivity increases with increase of temperature, whereas it was decreasing in the case with increase in temperature in the case of metals. Passage of current through ionic solution over a prolonged period can lead to change in its composition due to electrochemical reaction. So, in addition to above 5 parameters, there is also electrochemical reactions which changes due to passage of current through ionic solutions. So please note down, make a tabular column and compare the properties of electrical conductance through metals as well as electrolytic condenser. Measurement of conductivity of ionic solutions. We know that the accurate measurement of an unknown resistance can be performed on a Wheatstone bridge. So, a Wheatstone bridge is used to measure the value of an unknown resistance. But in the case of conductivity of ionic solution, there are two problems. First is the application of direct current changes the composition of the solution. Hence, for measuring the conductivity of ionic solutions, we use AC, that is alternating current source of power. Secondly, the solution cannot be connected to the bridge like a metallic wire or any other solid conductor, which we were using in the case of metallic conductivity or for measuring the resistance. Here, a specially designed vessel has to be used for measurement of conductivity of ionic solutions. The resistance of such a column of solution is then given by rho into L by A, that is equal to L by K into A. Before this sentence, please note the specially designed vessels which are used for measuring the conductivity of ionic solution. These vessels are called conductivity cells. Different types of conductivity cells are available in the market. but two types are shown on your screen. The first one is on the left side and has platinized platinum electrodes and which are connected through connecting wires as shown in the figure. Basically, these vessels consist of two platinum electrodes coated with platinum black. These have area of cross section equal to A and are separated by distance L. So the distance L is between two electrodes. This is another type of conductivity cell where here the area of cross section is here on the plates and its distance is L here. Similarly, two plates are here, left side and right side, and distance L is shown here. Therefore, the solution confined between these two electrodes is a column of length L and area of cross section A. The resistance of such a column of solution is then given by the equation R is equal to rho into L by A, where R is the resistance, rho is the conductivity, specific resistance, L is the length, and A is the cross section area. So we can substitute rho equals 1 over kappa. So this equation becomes R is equal to L divided by kappa into A. The quantity L by A in the above equation is called cell constant and it is denoted by symbol G star. So the G star is a cell constant whereas G was the conductance. The cell constant is usually determined by measuring the resistance of the cell containing a solution whose conductivity is already known. That means for measuring the resistance of the cell, we use the electrolyte with known conductivity. Like KCl solution is used as electrolyte. The value of such the conductivity of KCl solutions are depicted in the table number 2 shown on your screen. Here for different concentration, conductivity and molar conductivity are shown. For example, if you want to know the conductivity of KCl at 298.15 Kelvin at concentration of 1 mole per liter and its conductivity will be 0.1113 Siemens per centimeter and molar conductivity will be 111.3 Siemens centimeter square per mole. We will study about molar conductivity in the next slide. Thus, the cell constant G star is then given by the expression G star is equal to L by A. Here you see this is L by A is equal to G star, that is equal to R into kappa, where R is the resistance of the cell and kappa is the conductance. The value of conductance is noted, conductivity is noted from the table. Let it be equation 3. When once we know the value of the conductance cell constant, once the cell constant is determined, we can use it for measuring the resistance or conductivity of any solution. The setup for measurement of resistance is shown on your screen. Here, this is a bridge, Wheatstone bridge, having resistance R3 and R4, that is, and a variable resistance R1. So R1 is a variable resistance, R3 and R4 are resistance. R2 is an unknown resistance which is in the conductivity cell, and P is a suitable detector. This detector can be a headphone or other electronic device. When the bridge is balanced, that is, when no current passes through the detector or no current passes through P, the value of unknown resistance is given by R2 is equal to R1 into R4 by 3. Let it be equation 4. So I will repeat this. When the bridge is balanced, no current passes through the detector P. Under this condition, unknown resistance R2, that is the conductivity of the cell R2, equals R1 R4 divided by R3. Let it be equation 4. These days, inexpensive conductivity meters are available which can directly read the conductance or resistance of the solution in the conductivity cell. Once the cell constant and the resistance of the solution is in the cell is determined, the conductivity of the solution is given by the relation kappa is equal to cell constant divided by R. That is, cell constant is G star divided by capital R. Let it be equation 5. The conductivity of solutions of different electrolytes in the same solvent and at different temperatures differ due to charge and size of the ions in which they dissociate. The concentration of ions or ease with which ions move under a potential gradient. It therefore becomes necessary to define a physically more meaningful quantity called molar conductivity, which is denoted by the symbol lambda m. That is, lambda is Greek letter lambda. So I will read this sentence once again. Molar conductivity, which is denoted by lambda m, is related to the conductivity of the solution by the equation. The equation is molar conductivity lambda m is equal to kappa by C. Let it be equation 6. If in this equation kappa is expressed in Siemens per meter and the concentration C is expressed in moles per meter cube, then unit of lambda m are in Siemens meter square per mole. It may be noted that 1 mole per meter cube equals 1000 liters per meter cube into molarity, that is number of moles per liter, and hence lambda m, that is molar conductivity expressed in a Siemens centimeter square per mole equals kappa expressed in as unit is Siemens per centimeter divided by 1000 liters per meter cube into molarity, that is moles per liter. We can also express the units of concentration using the formula lambda m expressed in Siemens centimeter square per mole equals K kappa into Siemens per centimeter into 1000 cubic centimeter per liter divided by molarity, that is moles per liter. So this 1000 goes to the numerator and this meter also goes to the numerator. So we can take that and express in this form. Both types are used in practice and are related to each other by the equations 1 Siemens meter square per mole equals 10 to the power of 4 Siemens centimeter square per mole, or 1 Siemens centimeter square per mole equals 10 to the power of minus 4 mole. Let us solve some numerical problems. Question number 1. The resistance of a conductivity of cell filled with 0.1 mole per liter KCl solution is 100 ohms. If the resistance of the same cell when filled with 0.02 moles per liter KCl solution is 520 ohms. Calculate the conductivity and molar conductivity of 0.02 moles per liter KCl solution. The conductivity of 0.1 mole per liter KCl solution is 1.29 Siemens per meter. Please read the question once again. So here the KCl solution has got two different resistances. That is when its concentration is 0.1 moles per liter, it is 100 ohms. Whereas when the concentration is 0.02 moles per liter, then resistance is 520 ohms. We have to calculate the molar conductivity of 0.02 mole per liter KCl solution. The conductivity of 0.1 mole per liter KCl solution is given. Okay, we have to find the second case. Let us solve it quickly. The cell constant is given by the relation cell constant is equal to G star is equal to conductivity into resistance. That's equal to 1.29. That is conductivity is 1.29 Siemens per meter into 100 ohms. That is equal to 129 per meter. So the cell constant is 129 per meter, or it can also be written as 1.29 per divided by 100, 1.29 per centimeter. So conductivity of 0.02 moles per liter KCl solution is given by cell constant divided by resistance. That's equal to G by R. So G star is cell constant. Here also it is G star by R. That is equal to 129 divided by 520 is equal to 0.248 Siemens per meter. So concentration of 0.02 moles per liter. So that is equal to 1000 into 0.02 into moles per meter cube, and converting it to meter cube, that becomes 20 moles per meter cube. So we have converted mole per liter into mole per meter cube here in this step. So molar conductivity lambda m is equal to kappa by C, where lambda m is the molar conductivity, kappa is the conductivity, and C is the concentration. So values are given. Conductivity we have calculated as 0.248, or that is equal to 248 into 10 to the power of minus 3 Siemens per meter. So this we have converted into Siemens per meter, and the denominator is 20 moles per meter cube. So that is equal to 124 into 10 to the power of minus 4 Siemens meter square per mole. So in the using this previous step, we have calculated the molar conductivity. So alternatively, we can find out the conductivity kappa in another method, that is 1.29 cell constant by resistance, that is equal to 1.29 divided by 520 is equal to 0.248 into 10 to the power of minus 2 Siemens per centimeter. So lambda m, that is molar conductivity, is equal to kappa into 1000 centimeter cube per liter into molarity per molarity, that is equal to 0.248 into 10 to the power of minus 2 Siemens per centimeter into 1000 into centimeter cube per liter divided by 0.02 moles per liter, that comes to 124 S centimeter square per mole. So please pause and note down and make calculations, verify, cross check the calculations. Next question, the electrical resistance of column of 0.05 moles per liter NaOH solution of diameter 1 centimeter and length 50 centimeter is 5.55 into 10 to the power of 3 ohms. Calculate its resistivity, conductivity and molar conductivity. Please read the question. Pause the video and read the question again and note down all the given parameters. Let us answer. First we have to calculate area. Area is given by pi r square. Here the radius diameter is given 1 centimeter. Radius will be diameter by 2. That is 1 centimeter divided by 2 is 0.5. So therefore area will be pi. The value of pi is 3.14 into r square is 0.5 whole square. That is centimeter square. Area is in centimeter square. That is equal to 0.785 centimeter square. Converting into meter, it will be 0.785 into 10 to the power of minus 4 meter square. So length is given as 50 centimeters and that we are converting into meters as 0.5, that is divided by 100. R is equal to rho L by A, where R is the resistance, rho is the resistivity, L divided by A. So substituting the values, the value of R is given, area we have calculated, length also we have calculated. Substituting the values, we get 87.135 ohm centimeter. So therefore conductivity, kappa is given by 1 over rho by definition, 1 over rho per centimeter into 1000 centimeter cube. That is equal to 1 divided by 87.135 Siemens per centimeter or 0.01148 Siemens per centimeter. So this is simplifying. So molar conductivity by definition, lambda m is equal to kappa into 1000 divided by concentration, centimeter cube per liter. So substituting the values of kappa and C concentration, we get the value of molar conductivity as 229.6 into 10 to the power of minus 4 Siemens meter square per mole. So we can adopt this method or directly from this method. So these here the calculated values are shown. Please do the calculations once again. Variation of conductivity and molar conductivity with concentration. Both conductivity and molar conductivity change with the concentration of the electrolyte. Conductivity always decreases with decrease in concentration for weak as well as strong electrolytes. This can be explained by the fact that the number of ions per unit volume that carry the current in a solution decreases on dilution. The conductivity of a solution at any given concentration is the conductance of one unit volume of solution kept between two platinum electrodes with unit area of cross section and at a distance of unit length. So I will repeat this. The conductivity always decreases with decrease in concentration both for the weak as well as strong electrolytes, which can be explained by the fact that number of ions per unit volume which carry the current in a solution decreases. The number of ions decreases on dilution. The conductivity of solution at any given concentration is the conductance of one unit volume of solution kept between two platinum electrodes with unit area of cross section and at a distance of unit length. Thus, in the equation G is equal to kappa A by L, V equals K. Both A and L are unity. So, in this equation, if A is equal to 1 and L is equal to 1, G is equal to kappa. Molar conductivity of a solution at a given concentration is the conductance of the volume V of the solution containing 1 mole of electrolyte kept between two electrodes with area of cross section A and distance unit length. Therefore, we can write the molar conductivity lambda m equals kappa A by L. That is equal to kappa, because L is equal to 1 and A is equal to V, that is volume containing 1 mole of electrolyte. Thus, we can write this equation as lambda m, molar conductivity, lambda m is equal to kappa into V. Let it be equation 7. Molar conductivity increases with decrease in concentration. So, as the concentration decreases, the molar conductivity also increases. This is because the total volume V of the solution containing 1 mole of electrolyte also increases. The total volume increases. It has been found that the decrease in kappa on dilution of solution is more than compensated by increase in its volume. Physically, at a given concentration, lambda m can be defined as the conductance of electrolytic solution kept between electrodes of a conductivity cell at a unit distance, but having an area of cross section large enough to accommodate sufficient volume of solution that contains 1 mole of electrolyte. When concentration approaches zero, the infinite dilution of molar conductivity is known as limiting molar conductivity, and it is represented by the symbol lambda naught m. So, limiting molar conductivity is represented by the symbol lambda naught m, subscript 0 and subscript m and superscript 0. Let us quickly summarize conductivity in electrolytic solutions as well as study the effect of dilution. The table on the screen shows the various properties associated with electrolytic solutions, the formulae, units, and the effect of dilutions. Conductivity G, capital G, equals 1 over R, where R is the resistance. That is also can be written as A over rho into L, where rho is the specific resistance, A is the cross-sectional area, and L is the distance between the electrodes. That can also be written as kappa into A by L, and its unit is ohm inverse or Siemens S. The conductivity G increases as a large number of ions are produced due to dilution. The specific conductance kappa is given by the relationship kappa is equal to 1 over rho. That is 1 over rho is 1 over specific resistance, that is equal to G into L by A. Its unit is Siemens per meter or Siemens per centimeter. So specific conductance kappa decreases as the number of ions per cubic centimeter decreases. The molar conductivity lambda m, given by the formula lambda m is equal to K into V, where V is the volume, or that can also be written as kappa into 1000 divided by m, where m is the molarity. Its unit is Siemens centimeter square per mole or Siemens meter square per mole. The molar conductivity lambda m increases with dilution due to large increase in volume. Molar conductivity increases with decrease in concentration. This is because the total volume V of the solution containing 1 mole of electrolyte also increases. The figure on the screen, the right hand side, shows the variation in lambda m with concentration. It is different for strong electrolytes and weak electrolytes. Hence, the variation lambda m with concentration is different for strong and weak electrolytes. In the case of strong electrolytes, lambda m increases slowly with dilution and can be represented by the equation lambda m is equal to lambda m naught minus A into C to the power of half. It can be seen that if we plot lambda m against C to the power of, we obtain a straight line with intercept equal to lambda m naught and the slope is equal to minus A. The value of the constant A for a given solvent and temperature depends on the type of electrolyte, that is the charge on the cations and anions produced on the dissociation of the electrolyte in the solution. Thus, NaCl, CaCl2, MgSO4 are known as 1-1, 2-1 and 2-2 electrolytes respectively. All electrolytes of a particular type have a same value for A. Here, A is a constant. It is a slope. For weak electrolytes, like acetic acid, have lower degree of dissociation at higher concentration. For such electrolytes, the change in lambda m with dilution is due to increase in the degree of dissociation at any concentration C. If alpha is the degree of dissociation, then alpha is equal to lambda m by lambda m naught. In case of weak electrolyte like CH3COOH, lambda m increases appreciably with decrease in concentration. As we move from right to left, that is toward the center origin, the concentration decreases. This is in the case of weak electrolyte like CH3COOH, lambda m increases appreciably. Lambda m, here you see, please, as the concentration reduces, lambda m increases appreciably with decrease in concentration. because both the number of ions as well as the mobility of ions increases with decrease in concentration, that is on dilution. Kohlrausch's law of independent migration of ions. Kohlrausch examined lambda naught m values for a number of strong electrolytes and observed certain regularities. He noted that the difference in lambda m naught of the electrolytes NaX and Kx for any x is nearly constant. Kohlrausch's law states that the limiting molar conductivity, that is, the limiting molar conductivity of an electrolyte can be represented as the sum of individual contributions of anions and cations of electrolyte. If lambda naught Na and lambda naught Cl minus are limiting molar conductivity of sodium and chloride ions respectively, then the limiting molar conductivity of sodium chloride is given by the equation lambda naught m of NaCl equals lambda naught Na plus lambda naught Cl minus. Let it be equation 8. In general, if any electrolyte on dissociation gives nu plus cations and nu minus anions, then its limiting molar conductivity is given by the relationship lambda naught m equals V naught V plus lambda naught plus V minus lambda naught minus. Let it be equation 9. Here lambda naught plus and lambda naught minus are limiting molar conductivities of cations and anions respectively. The values of lambda naught for some cations and anions are shown in table number 3. This is table number 3 on your screen. So here for all cations the values are shown in column number 1 and anions it is shown in column number 3. The values you can see lambda naught, that is in S cm square mole inverse, and lambda naught, that is S centimeter square per Siemen centimeter square inverse mole. So the values are shown here. Thus lambda naught plus and lambda naught minus are the limiting molar conductivities of cations and anions respectively are shown in the table. The values of lambda naught for some of the cations and anions are shown in table number 3. Applications of Kohlrausch's law. Using Kohlrausch's law of independent migration of ions, it is possible to calculate lambda naught m for any electrolyte from lambda naught of individual ions. Moreover, for weak electrolytes like acetic acid, it is possible to determine the value of its dissociation constant once we know lambda naught m and lambda m at a given concentration C. Now we'll take up some work examples. Calculate the value of lambda naught m for CaCl2 and MgSO4 from the data given in table 3. That is table 3 in the earlier slide. You can copy down the values. We know from Kohl-Rausch law that lambda m of CaCl2 is equal to lambda naught of Ca2 plus twice of lambda naught Cl minus, because Cl2 there are two ions. Therefore, substituting the values from the table, we get the answer as 271.6 S centimeters square per mole. Similarly, for the case of MgSO4, it is given by lambda naught Mg2 plus lambda naught SO4 2 minus. So the value here is the values, substituting the values, given values, the values obtained from the table 3 for Mg and SO4, we get the result as 266 S centimeter square per mole. Question number 4. Lambda naught M for NaCl, HCl and NaC are 126.4, 425.9 and 91.0 S centimeter square per mole respectively. Calculate lambda naught for HAC. Here the lambda naught, the value of lambda naught is given. We are required to calculate the value of lambda naught. So again, using Kohl-Rausch law, we can substitute the values of lambda H plus lambda naught AC. Substituting the given values, we can get 425.9 plus 91.0 minus 126.4 S centimeters square per mole. That is summing up, we get 390.5 S centimeters square per mole. Please note here, we have to subtract the value of lambda naught M for NaCl. Question 5. The conductivity of 0.001028 mole per liter acetic acid is 4.95 into 10 to the power of 5. Calculate its dissociation constant if lambda naught M for acetic acid is 390.5 S centimeter square per mole. So lambda M is equal to kappa by C. This is by definition, that substituting the values, given values, we get in formula the answer is 48.15 S centimeter cube per mole. So the dissociation constant alpha is equal to delta M by delta M naught. That is equal to 48.15 divided by 390.5. That is simplifying, we get 0.1233. Alpha is a constant, hence there is no unit here. Kappa is equal to C alpha square into 1 divided by 1 minus alpha. That is equal to kappa is 0.00108 mole per liter into alpha is 0.1233 as we have calculated here, whole square divided by 1 minus 0.1233. The answer simplifying, we get 1.78 into 10 to the power of minus 5 mole per liter. Multiple choice questions. Question number 1. The specific conductivity of n by 10 KCl solution at 20 degrees centigrade is 0.0212 per ohm per centimeter, and the resistance of the cell containing the solution at 20 degrees centigrade is 55 ohms. The cell constant is 4 options are given. You have to calculate and mark the correct answer. You please do it, pause the video and do it and mark your answer. I will also do the explanation simultaneously. We know that kappa is equal to conductance into L by A. So L by A equals kappa divided by C, that is equal to 1 by C is R. So kappa into R. So therefore the cell constant G is equal to L by A is G star, that is equal to 0.212 into 55, that is equal to 1.166 per centimeter. So this answer is given in as option B. Please mark it. Next question is, electrical conductance through metals is called metallic or electronic condenser and is due to the movement of electrons. The electronic conductance depends on. So here this is the conductance through metals. Four options are given. Option A, nature and structure of metal, the number of valence electrons per atom. Option C, change in temperature. Option D is all these, all the three above. So you please study it and mark your answer. Meanwhile, I will also give the explanation. So the electrical conductance through metal depends on the nature and structure of the metal, number of valence electrons per atom, as well as change in temperature. So it includes all. Option D is the correct answer. Next we will take question number 3. Units of the properties measured are given below. Which properties has not been met correctly? So you please study it. Four options are given and you have to remember that specific conductance is Siemens per meter and this is given in option C. Next question. The molar conductivity of 0.15 m molar solution of KCl is at 298 Kelvin is 0.0152 Siemens per centimeter. So four options are given. So you please go through it. I will read the question once again. Molar conductivity of 0.15 m solution of KCl at 298 if its conductivity is 0.0152 s per centimeter will be. So you have to make some calculations and calculate the molar conductivity. We know that delta M is equal to K into 1000 divided by M. So it is given kappa is equal to 1.821 into 10 to the power of minus 5 into 1000 divided by 0.15. Simplifying, we get the answer as 101 per ohm centimeter square per mole. So 101 answer is appearing as C. Next question. The molar conductivity is maximum for the solution of concentration. So four concentrations are given. A 0.004 m, 0.002 m, option C 0.005 m and option D is 0.001 m. So maximum concentration is 0.005 and the lowest is 0.001. So molar conductivity is maximum because molar conductivity is inversely proportional to the molarity. So it is maximum for the minimum, that is option D. MCQ. Then next, specific conductance of 0.1 m NaCl solution is 1.01 into 10 to the power of minus 2 per ohm per centimeter. Its molar conductance in ohms inverse Cm square mole inverse is, four options are given. You have to make calculation and calculate the molar conductance. Delta M is equal to K into 1000 divided by M. So here it is given NaL solution is 1.01 into 10 to the power of minus 2 into 1000 divided by m. M is 0.1 m. This is given. So simplifying, we get 1.01 into 10 square per ohm centimeter square per mole. And this answer is available in option A. Please mark it. Which of the following statement is correct regarding variations of molar conductivity with concentration? So read the options. Molar conductivity decreases with decrease in concentration. The variation in molar conductivity of strong weak electrolyte is same. Molar conductivity increases with decrease in concentration. When concentration approaches zero, the molar conductivity is known as conductance. So the which statement is correct? So you have to examine and mark molar conductivity increases with decrease in concentration. Two solutions X and Y electrolytes are taken in two beakers and diluted by adding 500 ml of water. Delta M for lambda M of X increases by 1.5 times while that of Y increases by 20 times. What could be the electrolytes? So X, option A is X is NaCl, Y is KCl. Option B is X is NaCl and Y is CH3COOH. Option C is X is KOH and Y is NaOH. And option D is X is CH3COOH and Y is NaCl. Please read the question again and mark your answer. Meantime, I will give the explanation. Electrolyte is strong electrolyte. As on dilution, the number of ions remains same. Only interionic attraction decreases and hence not much increase in lambda m is seen, while lambda m for a weak electrolyte increases significantly. So therefore the correct answer is B. When water is added to an aqueous solution of an electrolyte, what is the change in the specific conductivity of electrolyte? Conductivity decreases, conductivity increases, conductivity remains same, conductivity does not depend on number of ions. So we have to change when water is added to aqueous solution of an electrolyte, what is the change in specific conductivity of the electrolyte? Conductivity decreases because number of ions per unit volume decreases. So option A is the correct answer. Next section. Limiting conductivity of Na bar is four options are given and using Kohlrausch's law you have to calculate the identify the limiting conductivity. So you have to remember that m delta lambda naught m Na bar equals lambda naught m NaCl plus lambda naught m Kbr minus lambda naught m KCl. Please mark the answer B as the correct answer. With this we come to the conclusion of conductance of electrolytic solutions. Next lecture, that is lecture number 4, we will deal with electrolytic cells and electrolysis. Till then, goodbye.